Hi everybody, I wanted to do this short lesson as a supplement to the first couple of pieces of this redox chapter. I wanted to make sure you had a clear understanding of the oxidation numbers and recognizing the processes of oxidation and reduction a little bit more than what you might have seen in the other videos. So I'm going to go through some examples. Some of these are actually examples from the Castle Learning assignment that I have related to this topic, so this is a good help for you. When you're looking at figuring out the oxidation numbers of substances, of elements that are in compounds and things, there are rules that you have to follow. A lot of these are really related to when we did formula writing back in the day, or you were doing the crisscross and figuring out charges. And those rules were covered, in the first lesson. Main things are if you have a lone element, its oxidation state is going to be 0. So if it's just magnesium hanging out, its oxidation state is 0. If it's a diatomic, if it's one of those Brinkelhoff elements, so let's say it's bromine, Br2, the oxidation state of each of the bromines is 0. So it doesn't matter what the subscript is. It doesn't matter if it's in an equation and it said like 3 Mg. What's the oxidation state of Mg? 0. It's by itself. Okay? If there are multiple elements in a compound, the sum of all their oxidation numbers has to add up to 0. So if you have, let's say sum of oxidation numbers is 0. So if you had something like carbon dioxide, all of the oxidation states of the carbon and the two oxygens have to add up to 0. So because carbon has multiple oxidation states, you would go with the rule that you have established for oxygen. So each of those oxygens' oxidation states is -2. There are 2 of them, so the oxygen side is -4. Which means the carbon side has to be +4. If you're dealing with an ionic compound, like, let's say this. So nickel has multiple oxidation states, and chlorine also has multiple oxidation states. But when you're dealing with those halogens, those group 17 elements, and it's the second, if it's the last element in the compound, you go with the top oxidation state, and the top oxidation state of chlorine is -1. There are 2 of them, so the chlorine side is -2 altogether, which means the nickel side has to be +2 in order for those numbers to add up to 0. So you're kind of just like working back and forth along a number line. So I'm going to work through a couple, examples of equations and things and how to track oxidation states. The big thing is knowing your definitions. So the definition of oxidation is when something loses electrons. So that's the Leo part. And reduction is when something gains electrons. So all we're dealing with here is number of electrons changing. That's the GR part. Okay, so it seems kind of weird, like, oh, I'm gaining something. How am I being reduced? Well, the charge, the oxidation number is getting reduced because if you gain electrons, your charge goes down. It becomes more negative. Moving in the opposite direction, if I lose electrons, I'm losing things that are negative, my oxidation number is going to become more positive. So if I had something like magnesium on the left side in the equation by itself, its oxidation state was 0, but by the time I get to the right side of the equation, it has a +2 oxidation state. Since its oxidation state became more positive, that would be an oxidation process. And if I had something like oxygen, which starts out as an element and then it turns into an ion, by itself, 0 for oxidation states, and it changes to a -2, well, becoming more negative means that you're getting reduced. So let's look at this in terms of some equations. So the first, one other thing I want to look at before I do an equation with you. This was one of the Castle Learning questions, actually. It asks for the oxidation states of each of the nitrogens in this compound. Okay, so this is ammonium nitrite. This is made up of 2 polyatomic ions, the ammonium ion and the nitrite ion. So we're going to look at reference table E for this one that has your polyatomics on it. So when ammonium is on table E just by itself, it's NH4 + 1. And the nitrite ion is NO2 - 1. So what that means, when we have a polyatomic ion like this, and it has a charge written next to it, that means that the oxidation state of that nitrogen and the oxidation states of all 4 of those hydrogens is adding up to +1 altogether. It's not adding up to 0. It's adding up to +1. Why? Because the charge is written there. Same thing with this nitrite. That nitrite collectively has a charge of -1. So the oxidation state of that nitrogen and those 2 oxygens has to add up to -1. So let's look at how this works for this particular question. Okay, so we don't have a rule for nitrogen. Nitrogen has like 7 different oxidation states listed on the periodic table. So we're going to do hydrogen first, okay? Because hydrogen has rules. Hydrogen's usually a +1 unless it follows a metal. Nitrogen's not a metal. So each of these hydrogens has a +1 oxidation state. And there are 4 of them, so that totals a +4. Now, what does that nitrogen have to be for its oxidation state in order for that nitrogen's oxidation state plus the +4 charge for all of those hydrogens to add up to +1? Okay, so what plus +4 equals +1? It would be -3. So the oxidation state of that nitrogen is a -3. So look at the math again. The -3 for that nitrogen plus the 4 +1s for those hydrogens adds up to a total of +1, which is the charge of the polyatomic ion. For the nitrite ion, same deal. Nitrogen has too many oxidation states, so leave it. Oxygen has a rule. It's usually a -2 unless it's in a peroxide. This is not. So this is a -2. And there are 2 of them. So the oxygens add up to -4. So what does this nitrogen have to be so that when it adds to the -4, you end up with a total of -1? Well, that would have to be +3. So +3 plus -4 is -1. So those are the 2, that would be the answer to that question. It's asking what's the 2 oxidation states for the nitrogens in that compound. So the first nitrogen's oxidation state is -3. The second one is +3. So let's look at some changes in oxidation state. Let's do something simple here. Let's look at copper. Now this equation is like the shortened version. They left out the elements that did not undergo oxidation or reduction. We call those spectator ions. So this equation is called the net ionic equation. It only is showing the parts of the equation that we're concerned with, the ones that are undergoing changes. So let's look at the oxidation states of these elements. So this copper is by itself, right? There's nothing with it. It doesn't have any charge written next to it. So its oxidation state is 0. Now let's look at the copper as it appears on the right side, on the product side of the equation. On the product side of the equation, that copper has a charge written next to it of +2. It doesn't matter if you do 2 plus, +2, whatever. But so look at the change that occurred here. If copper went from a 0 charge to a +2 charge, what happened to it in terms of electrons? Remember, electrons are negative. So if my charge becomes more positive, that means that I lost electrons. And what is the process of losing electrons? Oxidation. So the copper was oxidized. Now, look at the silver. The silver, on the reactant side, I have the plus there with no number. It's understood to be 1. So I have 2 silvers with a +1 charge. Okay, so each silver is a +1. Now look at the silver on the product side. There's no charge written next to it, so it's a 0. So look at the change that happened with the silver. Silver went from a +1 to a 0 twice because there's a 2 coefficient there. So 2 silvers went through this process. So there's a gain of 1 electron apiece. And we know that's going to be times 2 because there's a 2 coefficient there. So what's the process of gaining electrons? If my number's going down, right? It went from a +1 to a 0. I'm moving in the negative direction. So what happened to me in terms of electrons? Well, I must gain electrons if I became more negative, and that process is reduction. you cannot have the same process occurring in two different places. Like I can't say, oh, copper was oxidized and so was silver. You can't do that. This process is an exchange of electrons. Okay, I can't be like, oh yes, I'm going to go to the store and they are going to give me money and I'm going to take things with me. There's got to be an exchange here. Someone's going to lose and someone's going to gain. Okay, you cannot have the same process happening in two different places. You can have one element going through two different processes, and that's the case sometimes, and that's a little past where we need to go right now. Okay, so that we have this loss and gain of electrons. Here's another example. Now, since we're in a redox unit, you know that this has to be a redox reaction, but earlier in the year we were classifying reactions. We also could classify this reaction as being a different type, and it would be perfectly fine. You could also classify this reaction as being a single replacement reaction. Right? We have the nickel replacing the hydrogen. So if I took a piece of nickel and I dropped it into hydrochloric acid, I would get those hydrogen bubbles. I could trap it in a test tube and get that fun popping sound. That's a single replacement reaction. It also happens to be a redox reaction. How do I know it's a redox reaction? An easy way to spot a redox reaction is you look for an element that's by itself on one side of the equation and it's not by itself on the other. Now, if you didn't see the nickel, you could see the hydrogen who had the same thing going on. It's by itself on one side of the equation, it doesn't matter which side, and it's not by itself on the other. Now let's look at the changes in the oxidation states that are occurring here. So the nickel reactant is by itself. That means its oxidation state has to be 0. Now look at the product side for the hydrogen. The hydrogen is by itself on the product side, so its oxidation state is 0. Now, looking at the nickel on the product side, since it's in a compound, we know its oxidation state can't be 0 anymore. So that's like why we can picture this as being a redox reaction. Like, oh, it was a 0. When it's in a compound, it can't be a 0. So it's got to be a redox reaction. So let's look at what the nickel should be. Now, because nickel has multiple oxidation states, we'll look at the chlorine. Chlorine being a halogen that comes at the end of a formula, I can use the top oxidation state, which is -1. -1 times 2 of them is -2. Which means that the nickel has to be a +2 because this compound overall has to add up to 0. So that means this nickel's oxidation state is +2. So nickel went from a 0 charge to a +2 charge for its oxidation state. Now let's look at the HCl. Again, hydrogen can be a +1 or a -1, but since it's at the front of the compound, it's going to be a +1, which means the chlorine has to be a -1 to add up to 0. So we see that the chlorine did not change its oxidation state. Chlorine started as a -1 and it ended as a -1. So that is a spectator ion. Okay? It does not participate in the reaction. But the hydrogen obviously does. The hydrogen went from a +1 oxidation state to a 0 oxidation state. So if we had nickel going from a 0 to a +2, and we had hydrogen changing from a +1 to a 0. So which element underwent which process? Because we can't have both of them doing the same thing. Well, if hydrogen became more positive, that means that it lost electrons, which means it was oxidized. And since hydrogen went from a +1 to a 0, its charge went lower, gain electrons. That makes it more negative, right? It moved in the negative direction, so that was reduced. Okay, so remember, if your oxidation number is moving in the positive direction, you're losing electrons, which means you're being oxidized. If your oxidation number is moving in the negative direction, that means you're gaining electrons, and that's going to be reduced. So I hope that gave you a little more clarification before you jump into the CASA learning.